Part B, efficient polynomial evaluation. B.1, evaluate the polynomials. First, it's a simple problem. So when we start, we want to look at a simple computing problem. Yeah. But at the same time, so I try to explain several problem-solving, thinking-related considerations. First, let's get our problem first. Problem description. Problem 1, evaluate a polynomial. Given a polynomial, we use this, our standard representation. Here you can see it's a general case. Later, we will try to work on some very large polynomial. So you can imagine this n number could be very large. With coefficients given, all these coefficients given as the input. Array data. But we also need to have the value for this variable x. But each time we can change a different value for this variable x. Coefficients, relatively stable. So we do not change frequently. But we need to change the x value frequently. Question: how to evaluate p of x efficiently? The efficiency is our biggest concern here. Correctness, we don't worry about correctness. We know most people can find the correct value easily, right? But for the efficiency, then we need to have a lot of discussion on this efficiency here. Here, let me give you the reference in the textbook. So this one, I took this section 6.5. This problem I took from section 6.5. This one, I didn't follow the natural order of the textbook. But after that, most of the other materials, I follow the order. The reason I took this problem at the beginning, because first, this problem is not hard. Evaluate a polynomial, it's very simple. But another thing is also there is a very smart algorithm that can solve this problem efficiently. And after I finish this problem, we can do a programming project. So we can do a quick start. Because doing a project takes a lot of time. So we want to start as early as possible. So that's the reason I want to start it as our first computing problem. All right. First try. So before we have any idea solving this problem, so let's just find a solution first. In our first try, we don't worry about if this method is efficient or not. We just want to get a correct method, correct way to solve the problem. And let us worry about efficiency later. After we get a correct solution, then we look at the efficiency issue. We just use the straightforward algorithm. Everyone knows how to evaluate a polynomial, right? So you have no problem, because when you find the value of this polynomial, typically you just do additions and multiplications, right? all of you know how to do additions and multiplications. You can write a program easily to do additions, multiplications in certain natural order and find its value, correct value. Yeah. Because we're pretty sure the value should be correct. Okay, yeah. So that's our first try. Yeah. Work on each term. But yeah, when you do the specific operations, do you need to work on each term? So this is a typical term. Representation for a typical term. Yeah. So here we take a general representation as the representative. Yeah. Here we can use this one term. We can represent any of the other terms. So that's a common way. Yeah. We just take a representative. It is a general term and it covers all the other terms. Yeah. Here, when you look at this representation, a coefficient times x to the kth power, yeah, we only need to do multiplications, right? We don't need to do any addition. Yeah. My first question for you here, can you tell me how many multiplications do we need to find the value of this term? Anyone can give me a number? Yeah. Just give me a number. Which one you feel the best? 2? Oh, 2. Look at this k here. Exponent. This k could be a large number. Let me say if this k equals 100. Can you use 2 multiplications to give me the value a sub k times x to the 100 power? Right? Exponent. Right? Can you tell me how many multiplications? Anyone has?
You'll have to do at least k multiplications.
Yeah, all right. Pretty good. Yeah, at least. Oh, you told me at least k. That means could be more than k, right?
Yeah, so k plus 1 for the a.
K plus 1. Oh, so you give me, yeah. So here, I heard a number k plus 1 here. Any other student could give me different answer, so we can compare. Okay, good. All right. Now here, possible, yeah, 2 possible numbers here. Yeah. At this point, I allow you to make a guess. Yeah. So in our problem solving, actually guessing is a very important capability. Very important ability. Good guess. You want to make good guess. When we say guess, it's not necessary it must be correct. We allow some error in your guess. Yeah. The purpose of the guess, we just want to get a close answer, not necessarily exact answer. Okay. Here, let's treat the numbers you gave me here, 2 different guesses. Yeah. We want to see which one is the answer. Okay, all right. So here I want to give you some simple problem solving strategy. The first one. When we do counting here we're doing counting, right? We count the number of multiplications. That's a counting problem. Okay. Here the strategy we want to take here. Do experiments. Here. Do some experiments. Yeah. All right. When we do experiments, we want to try some relatively small number k. Yeah. Let's say k equals 1. a1 times x to the first. How many multiplications we need here? a1 times x to the first. How many multiplications?
1.
Good. 1. Yeah, only 1. Second. Yeah, second. When k equals 2, a2 times x squared. How many multiplications do you need? a2 times x squared. Multiplications.
2.
2. Correct. All right. Yeah. 2 simple experiments, right? After these 2 simple experiments, can you tell me for the general k, how many? Can you tell me how many? When k equals 1, it's 1. When k equals 2, it's 2. Can you find some rule? Some obvious rule you observed from these 2 simple experiments?
So it'll just be k then?
K, that's correct. So definitely k plus 1 is not correct, right? Yeah, because when k equals 1, your k plus 1 is not correct, okay? When k equals 2, your k plus 1 also not correct. If 1 is wrong, you can cross out, okay? Yeah. So k is correct, although you can do more experiments. So, you know, here you can see our first problem solving strategy. You just do some simple experiments. You can find some rule after it. All right? Yeah. All right. Conclusion, you need k multiplications to calculate individual terms with subscript k. Yeah. All right. Next, is your algorithm efficient? Or is this the best answer you can get? Can we do better than this one? Because our goal, we want to find the best way to find a solution. Yeah, for this class, we always want to find the best solution. If your solution can be improved, then we will try our best to improve the solution. Here, we want to ask this question. Can we use fewer than k multiplications to find the value of this term? Now, think about it. Okay? Yeah. All right. So here, when we talk about the algorithm efficiency, we may like to find a performance number of this algorithm. Yeah. Because if you do not use any specific number, when you talk about if this algorithm is efficiency or not, usually it is quite subjective, right? Quite subjective, yeah. Because one of you say it's efficient, it's not for a different student. That student may feel not that efficient. Yeah, it's quite subjective. Yeah. We want to have some objective way to describe the efficiency, right? Yeah, yeah. So that's the first consideration. So when we need to use a concrete performance number, we want to make the subjective thing to some objective thing. Yeah. So that's the first consideration. Yeah. All right, we will discuss this issue later. Yeah. Another question here. Are we satisfied with the solution? Yeah. Yeah. Because at this point, yeah, from your perspective, if you only know the single solution, yeah, I believe most of you only know this is the only way you know to calculate this term. If you do not have any other options, that's the only one you can take. No matter you satisfied or not, that's the only way you can take, right? Yeah. So to answer this question, we want to see if we have a different solution or not. Yeah. Yeah. Someone, you need to check your microphone. Yeah. Making a noise. Yeah. Try to mute your microphone. Yeah. Oh. Yeah. Let me look at Jed. Yeah. All right. Yeah. Good. Yeah. Okay. Yeah. All right. Yeah. Let me show you a special case here. Oh, here the problem. Yeah. Remember. Yeah. What if I do some action with the Zoom, then my PowerPoint slides, some functionality disabled. So I need to restart to enable it. Yeah. So that's the, some problem. Yeah. All right. So next time I can do this way. I need to use two computers. Okay. On one computer, I can do some Zoom actions. Yeah. But on my presenting machine, so I should not do any action related to the Zoom. Then I can, run it smoothly. All right. So here we do not know how bad it is. So we can not answer the question if we are satisfied with the solution or not. All right. So let me show you the simplest case. Yeah. Let you see it's possible to get a different solution. All right. So let's just look at it. Let's ignore the coefficient part. Let's only look at x to the kth power. Okay, it's a monomial. For this monomial, we only take a special monomial, x to the fourth. It's a special one. Okay, yeah, it's a special one. First, because there is no coefficient, right? If we want to find its value, we do not need to do multiplication on that coefficient part. So we can save one multiplication. If we use the old way, I need to change the color. Yeah. Every time I restart, I need to change the color. All right. First, if we use our old solution, it should be k, but because there is a coefficient multiplication here we can save one multiplication for the coefficient. That means for this x to the fourth, by our old method, we only need 3 multiplications. Right? Yeah. 1, 2, 3. Yeah. Now let me show you a different way to calculate this value. First, we take one multiplication, 1 x times x. One multiplication, we get x squared. Okay. Second, we take our second multiplication, another one here, x squared times x squared, we get x to the fourth. Here you can see after two multiplications, we find its value. So the final answer is we just need 2 multiplications instead of 3 multiplications. Right? We do not really need 3 multiplications. We can save 1. 2. Here you can see by some special way, especially the second multiplication. X squared, because we have the x squared value. We just use x squared multiply itself. to get x to the fourth. We do not need to go through x cubed. We just bypass x cubed. So we can jump to x to the fourth in a faster way. In this way, you can see we can do better. We can do better. Think about that. Okay? So this simple example tells us we have more room to improve our first solution. We have some rule. If we explore very hard, we have some chance to get better solution. Think about that. Okay? All right. So let's do improvement. More effort on the improvement. All right. First, do we need an algorithm here? Yeah, algorithm. Some special way here. Some, smart way. Yeah. Do we need one? Yeah. Actually, our first try, although it's not a good method, but we can treat it is an algorithm. Our first try, it is an algorithm. Okay? So our first try, actually there is a name for it. So we called brute force. Brute force method. Okay? Yeah. So later we will discuss about this brute force method. Right. All right. So when our imagination is very limited due to lack of experience, at the beginning in the problem solving, it's very common we have no idea, right? Because you do not have a good understanding on the given computing problem. You do not know how to get started, right? Yeah. So we need to get some experience to understand our computing problem better. Yeah. All right. So here, at the beginning, how do you get a good understanding? So we want to do this brute force method. Brute force method typically means, so we do not need to use any special technique. Okay? Yeah. Just do it in a straightforward way. Yeah. Do it in a straightforward way. That's the brute force. No technique is needed. Okay? Like our first solution, it's a brute force method. Yeah. But when we do that, at least we get some experience, right? We can understand our computing problem a little more by working the first round. Yeah. All right. Here, we know to solve this problem, we only need to do additions and multiplications. So when we want to improve our solution, basically we need to manipulate these additions and multiplications. We need to try various ways to do the manipulation. All right. All right. Here, the question. Do we still have any room to manipulate the additions and multiplications? Here we need to use our imaginations. Yeah. Can you imagine some various ways to do different manipulations on our data? Here our data, coefficient data, and the x value data. Okay. So if you can use some quite different ways to manipulate the given data. Yeah. All right. Yeah. So more specifically here, the manipulation, it means we do this thing. We apply these operations, here, given order. So let's say, so what's the given order? Given order is because when you see this expression, there is a natural evaluation order, right? So when we learn in elementary school, so we know what is the default order to evaluate this expression, right? So we do multiplication first. So multiplication takes higher precedence over additions, right? So we know what's the default order to do the evaluations. Yeah. So the given order means that. But we have freedom to do evaluations in different ways, right? We have freedom. Yeah. We only need to make sure the final result is correct, right? Yeah, because at the end, we just want to get the same correct answer at the end. How do we evaluate? We have some freedom, to use different ways to do the evaluation. Yeah. In our previous simple example, that's the one of the simple ways we can change the evaluation order, right? Yeah. X squared times x squared. That's one special way. All right. Question. Do we have other orders to apply the operations? Other orders other than the default given order? Yeah, that's another question. If we can change, we can manipulate. That's the place we do the manipulations by changing the order of evaluation. How? The question, how to change? So we work on the order change. We want to have the same answer, but the intermediate steps, we can make some change in the intermediate steps. That's the order change regarding the applications and the multiplications. All right, so here, another thing, regarding the efficiency, because our goal, we want to make this algorithm more efficient. That's our goal, okay? Regarding the efficiency, how do you measure efficiency? How do you use a concrete number to tell people your algorithm is efficient or not? Here, this question, can we use the execution time? We just clock it. So we just look at the execution time when we run this program. Can we use execution time to tell people how fast is our algorithm? Here the question. First, this way is objective, right? Execution time, it's objective. It's a number, clock. We look at the clock, okay? It's objective, but it's unstable. Unfortunately, if you want to use the execution time, it's not a stable measure for the efficiency. Why not stable? Because people can use different machines to run the same program, right? Some machine, if you use some old, slow computer, you may get a slower execution time, right? If you use a supercomputer, multiprocessors, parallel computing, supercomputer, you can get much faster execution time, right? Yeah. So that's why we say from the hardware point of view, execution time is unstable. Also from the software point of view, it may not be stable software because different programmers implement the same algorithm. Yeah. Some experienced programmers can make it faster than those beginner programmers, right? If you do not have a lot of experience. So if you write a code to implement the same program, probably your program runs relatively slow. But another one with a lot of experience, yeah, so they know how to improve the total performance, overall performance, so they can do a lot of special treatment, yeah, so manage the memory more efficient, so many different ways to improve the coding. Okay, they can do faster. Yeah. So from the software point of view, execution time may not be stable. All right? Yeah. So here you can see, because if this execution time is unstable, we want to use a stable measure. So we don't want to choose execution time to measure the efficiency. Okay, yeah. So that's another important concept. Yeah. All right. Yeah. Yeah. So the goal for a stable, better measure for the efficiency, we want to make sure our efficiency number is always the same for different hardware devices or different software implementations, always the same number. In that way, we can say it is a stable measure. Okay? Yeah. All right. Yeah. Here, how to measure efficiency in a stable way. Yeah. Here, in this problem, we want to use the number of additions and the multiplications. Number of additions, number of multiplications. Yeah. Then we can fix this unstable problem. Because on different machines, the numbers are the same, right? You use the same number of additions, same number of multiplications. Yeah. For different programmers, although their implementations could be different, but if we talk about the same algorithm, the number of additions, number of multiplications are the same. So that's the stable measure. Yeah. Yeah. All right. So here you can see, yeah, we find a stable efficiency measure. Yeah. Yeah. But we will, because here there are two numbers, right? One number for additions, one number for multiplication. There are two numbers. So we need to find a better way to cover these two different operations. Yeah, later. Yeah, I will talk about this question later. Yeah. All right. Yeah. Here, in computer hardware implementation, additions and multiplications, the speed are different, right? We know additions running in a computer is much faster than a multiplication. Multiplication much slower than an addition. Yeah. So that difference we need to consider. Okay, we cannot treat the execution time used for one addition and one multiplication are the same. We cannot say that. Okay, yeah. the difference is pretty big. Yeah. All right. So to make it fair, right? To make it fair, when we incorporate additions and multiplications, so we need to make some reasonable assumptions here. Okay, yeah, to bridge the gap. Yeah, because we try to, try to bridge the gap between additions and multiplications. All right. What assumption we want to make? Yeah, each addition takes 1 unit of time. 1 unit of time. Okay, so that unit here we do not specify. So that unit, there is some number there. Yeah, some unit. Yeah. So here it's not important. How large is that unit? May not be very important. Yeah, but I can give you an idea a little bit. A few nanoseconds. You know nanosecond, right? Yeah, nanosecond. You know nanosecond, right? So that unit is a few nanoseconds. Okay, small number of nanoseconds. Okay, all right. Then each multiplication takes approximately 10 times of one addition. So 10 units of time. Okay, so that's approximately the difference scale between one addition and one multiplication. Here, this 10 to 1 ratio may not be very accurate, but approximately close to that ratio. Okay, so we just make this assumption in our discussion for convenience. 10 to 1 ratio. Okay, one multiplication approximately equals to the time used for 10 additions. Then we can, even the playground, right? We can do comparison. Yeah. Otherwise, how do you compare addition with multiplications? Right? It's hard. Yeah. But after this assumption, so we can do some relatively fair way to combine two different types of operations. Yeah. All right, B.2. Now we can estimate the cost. When we use the brute force method, what is the total cost? All right. Subproblem number 1, count the number of additions. Yeah. When you look at this formula for the given polynomial, can you tell me how many additions do we need? Just by the brute force method. Here, we do not change to other method. Just the brute force method. Can you tell me how many additions? Don't look at the multiplications, only additions. Can you guess a number? Yeah. The first, just make a guess.
N minus 1?
All right.
X.
I see.
X minus 1? No, it wouldn't be X minus 1. Never mind.
Do not use X, use N. Use N. Okay. I heard N minus 1 as one of your guesses. Any other guesses? Different?
Wouldn't it be?
Different number, different guess. I put here.
Is it N plus 1?
Okay. N plus 1 is any more different guess?
N.
N. Good. Here, typically we have 3 different guess answers. We want to determine which one is correct. Okay? All right. Do you know what simple method we should apply to fix this guess problem? Yeah. Only one of the 3 can be correct. The other 2 must be wrong. But how do we fix it? That's the question. Can we use our previous method by doing simple experiments? simple experiments. Okay, all right, yeah. So here, let me talk about some problem-solving skill here. Okay. The strategy, simple strategy in problem solving. Work on the easier parts first. Pick easier parts first. Yeah. For this particular question, there are two parts. Okay. Yeah. All right. Yeah. So, right. Yeah. What is the hard point here? Yeah. It's here. Yeah. The reason I ask you to make a guess, the hard part is, you see this expression, right? So we skip many terms in order to write the expression in a compact way. We skip many terms. Yeah. But when we use the expression, that make it hard to figure out the final answer, right? Because people get lost. How to keep track of your data when you see ... It's hard to keep track of the data, right? Yeah. Most people get lost with the ... expression. Yeah. All right. So here I want to give you a solution. Yeah. How to keep track of the data without getting lost. Yeah. All right. So here, how to find an effective way to keep track of those invisible terms. There are so many invisible terms, it's hard to keep track of them, but we need to find a simple, effective method to help us keep track of the data. Okay, yeah. So here, so let me introduce a counting technique. Yeah. So it's called counting by reference. Actually, it is based on our everyday life experience. In our everyday life, many times we do things by finding certain references, right? Yeah. Yeah. Something, if sometimes we need to, when we describe a location, we need to find a reference, like a building, like some road, some, traffic light. We use those things as references, right? Here, when we want to make some invisible, uncertain things more certain, we want to create, or we want to find appropriate references. So here, the counting by reference idea, let me describe it. The essence of this method, we want to discover some one-to-one correspondence between two mathematical objects. Yeah. So the one-to-one correspondence, right? So, yeah. Between two different mathematical objects, so that we can get a good references. Yeah. So let me describe the idea in this diagram here. Suppose we have two different objects. Here we mean some mathematical objects. So what's mathematical? Plus sign can be treated as a mathematical object, right? Yeah. Each term can be treated as a mathematical object, right? So object 1, object 2. We want to do one-to-one correspondence. Yeah. For object 1, it could be hard to count directly. Yeah. For example, when you count the number of additions, do you count the number of plus sign? Because each plus sign corresponds to one addition. If you can count the number of plus signs, you know you have that many additions. Yeah. So our first object, plus sign object. That's our object 1 here. Okay? Yeah. But that object, not easy to count. So what we want to find some object 2 that are easier to count. Okay, easier than object 1 for the counting. So what's the object 2 here? Can we associate the first plus sign to the subscript of the first coefficient, A1 coefficient? Can we associate the second plus sign to A2 x squared coefficient, and so on? Can we associate the last plus sign to A sub n coefficient? Is that one-to-one correspondence? One plus sign corresponds to exactly one subscript of the coefficient. Okay, yeah. So object 1, that's the plus sign. Object 2, subscripts. Okay, so how about that? That's the one-to-one correspondence. Plus sign, hard to count because the dot dot dot, hard to keep track of the data. But to count the object 2, is it much easier to count object 2? Because your object 2, you have consecutive integers starting from 1, 2, 3 consecutive integers. Then the last one is n. Tell me, how many subscripts do we have here in this list? Okay, in this list, because 0 is not included. There is no plus sign associated with A0. So we do not include 0 subscript in our list. So now can you tell me how many subscripts in the list? Answer: n consecutive integers, right? First n consecutive positive integers. So the answer, the number equals n. So when you count the second object, object 2, you can find the number easily. That's n. So this guess n is correct. N minus 1, n plus 1, both wrong. N is correct. Okay? Then we go back to our object 1. When we count the plus sign, we can say it's also n, because 1-to-1 correspondence. It should be the same number. Okay? When you establish 1-to-1 correspondence between two sets, set 1, set 2. Okay, two sets. Okay, now, another set plus, so many plus signs, all your plus signs. Yeah, but it's hard to keep track of how many of them. But you establish 1-to-1 correspondence between these two sets. Okay, yeah. So then we can say they should have exactly the same number of elements in these two sets. They are both finite sets, same number. So that's what I call counting by reference, because you find good reference. Object 2, good reference. Yeah. All right, yeah, look, yeah. So now, so you learn this special counting method. Simple, yeah, but effective. Later, we will use this method many times. All right. Okay. Yeah. Yeah. Do not include the first one. Yeah. Yeah. So here we ignore the first term, that is A0. This term ignored. Okay. Yeah. All right. The answer, n units of time, right, for the addition. Next, find the number of time units, but this time we need to solve our subproblem number 2. Count the number of multiplications. How many multiplications? Okay, all right. So here, we already find the answer here, right? The answer is K. So let's accumulate all those numbers, corresponding to all the multiplications. Yeah. From all the terms, here n plus 1 terms, but remember the first term, there is no multiplication. The first term, 0 multiplication. Okay, yeah. So only n terms we need to apply multiplications. Here, let me do the chart. Yeah. So for each term, the first term, 1, second term, 2, and so on. Yeah. So we need to add up all these n numbers. Yeah. Here, we know this formula. Yeah. The summation of the first n consecutive positive integers. So this is the formula. We'll just use it directly. Yeah. Yeah. So the total number of multiplications, 1/2 times n minus 1. Okay. All right. But finally, when we need to look at the number of units of time, we need to do one more step. So we need to look at the total number of units of time to do the brute force method. Total units of time. For n additions, the contribution from n additions, that's n units of time. The contribution from n times n plus 1 over 2 multiplications, we know each multiplication equals 10 units of time by our assumption. That's the assumption. So we need to multiply this number by 10. Yeah. Yeah. So that's 5 times n minus 1 units. So now we add up these two numbers to get the total number of units of time. So that is after some, simplification. So we get this expression: 5n squared plus 6n units of time for the brute force algorithm implementation of polynomial evaluation. Yep. So that is the performance number we want to use for the comparison. Yep. Because the reason we calculated this number, later we want to improve this algorithm. When we improve the algorithm, we will have a different performance number. So we will use our new performance number to do the comparison with this old performance. This is old performance number. New one with comparing with the old one. Okay? And if we want to see how large is the difference. Okay? That's the idea. All right. Okay. Question. Because next, after we get this performance number or efficiency number, next thing we want to improve our algorithm. We know by some simple experiment for x to the 4th, we know it can be improved. But we don't know how to improve it. The question is we don't know how to improve it. We know it could be improved. There is room for improvement. But the question is how to improve it. So let's move to our next part. Question. Can we reduce this number? Answer is yes, right? Based on our, x to the 4th. This simple example tells us the answer is yes. But we don't know how. The question is how. That's the hard part. How? Okay, So let's work on the how part. How to improve. improvement strategy. Yeah. Because on this how, we have a new problem to solve. So we need to use a different problem solving strategy. Okay? So here, some improvement strategy need to be considered. Yeah. Here, there are two parts to be improved on. So what two parts? Addition part and multiplication part. That two parts. When you do the improvement, do you want to work on, do you want to target the addition part, or do you want to target multiplication part, right? Yeah. So there are two options you can take. Here we have a strategy for this situation, improvement strategy. All right. So let me talk about that. Which part should we focus on when we have two parts? Yeah. In other computing problems, you may have multiple parts. Yeah. For this particular problem, we only have two parts. Yeah. It's relatively simple. So if I draw a diagram here, let me use the circle to represent the total time used. Yeah, total time used to calculate a polynomial. Okay, so I divide it into two parts. Yeah. The bigger part, the multiplication is the bigger part, m part. Okay, addition much smaller than multiplication part. A part much smaller than m part. Okay, yeah. All right. Here, how to determine which part should we focus on. So there is a specific strategy for it. Yeah. So let me talk about that first. Okay, yeah. Observation for the property. Yeah. First, we know the cost ratio. Unit cost for multiplication over unit cost for addition equals 10-to-1 ratio. Okay, already 10-to-1 ratio. And we also, other than the unit difference, for the number difference, multiplication, that is 5n squared plus 5n, and for the, addition, for the number much smaller, addition much smaller. Okay, yeah, unit much smaller, number also much smaller. So you can see overall the execution time spent on addition much smaller than execution time spent on multiplications. Huge difference, right? So that's our observation. All right. So which part do we have more room to improve? Okay. Yeah. Think about if the addition part very small, very tiny portion of the total execution time, you do not have much room to improve, right? For multiplication, you have, most huge, big portion in multiplication. So you have much larger room to improve your multiplications. That's the simple, intuition. That's the straightforward intuition, right? Yeah. Yeah. Addition part too little, so you do not have much room to improve it. Yeah. Multiplication, yeah, almost 99-something% execution time you spend on multiplication. So you have a lot of room to improve it. Okay? Yeah. All right. So the strategy, final conclusion for the strategy, we call it focus on the major part. Yeah. Major part, that's the multiplication part. The dominant, major dominant part, multiplication. The minor, tiny part for addition. Yeah. So we should not focus our resource, energy on the addition part. We should focus on our resource energy on the multiplication part. Yeah. That strategy was summarized as a famous rule in computer science. It's called Amdahl's law. Amdahl's law. Okay, Amdahl's law. Yeah. Okay. Amdahl's law. Okay, yeah. And Amdahl's law. Okay, that means when you have, so it talks about a general principle. When you need to improve the efficiency for certain computing task, okay, for certain general computing task, you should focus your investment or your resource on the most common part. Okay, most common part. Yeah, that's the Amdahl's law. Okay, yeah. I have remember I said in our first lecture, I will create many flashcards to summarize the main knowledge points of this class. Yeah. Amdahl's law, I created one flashcard for it. Okay, so at the end of this PowerPoint slides, you can see the Amdahl's law. Okay, so I describe it there. Yeah. All right. Conclusion: we should focus more on multiplications because that is the most common part, the major part. Yeah. All right. The strategy, specifically, it should be reduce the number of multiplications. Try our best to reduce the number of multiplications. How? That's another question. Right now, we make our decision on what direction to go. Right? What direction to go? We go along this direction, multiplication direction. Okay. How to get there? That's another question. Okay. So we will answer a sequence of questions one by one. Yeah. So another question we need to answer next. So the new question: how to reduce the number of multiplications? All right. Yeah. B.3, the key solution part of part B, Horner's rule. You will see our final solution to answer this question. That's the Horner's rule. Okay. All right. Yeah. So we just have a little more than 5 minutes. So let me, do some preparation part for the Horner's rule. Yeah. Yeah. We need at least 20 minutes to complete the Horner's rule. So let me use 5 minutes to do some simple preparation for the Horner's rule. Okay. All right. The strategy. When we try to work on the how part, how to improve it, how to improve the multiplication part. Yeah. The strategy: study a simpler case. Yeah. So what's the simpler case here? Yeah. Do simple experiments. Yeah. As we did before, just work on, the simplest possible data to get some experience. We need experience. Okay, yeah, here, let's do it. Discover certain property from the experiments. If we do not do anything, then it's hard to find anything, right? Hard to see anything. If you only just do your imagination, it's hard. Okay, yeah. So we need to do something concrete here. It is easier to do experiments when the data sizes are small. If the data size is large, think about if n equals 1,000, if I ask you to reduce the number multiplication for a polynomial with, degree 1000, it won't be easy, right? It's too hard, Yeah. So we work on small data sizes. Yeah. And we want to, after the experiment, we want to find or discover some critical property. Okay? Yeah. All right. Yeah. Here, let's do the work. Okay, let's do the work. We consider n equals 2. N equals 2. Yeah. That's simple, right? Yeah. Because if n equals 1, that's too simple, right? Yeah. We may not get anything meaningful. Yeah. If it's too simple, we may not get it. Something meaningful, right? So although we want to work on simple, smaller data sizes, but still we want to work on something meaningful. Okay? So that's the reason we choose n equals 2. Here, 3 terms, yeah, n equals 2. Yeah. So try to observe some property here. Property. So what's the property here? Okay, yeah. The property here is these 2 terms, they have a common factor. Common factor x. X is the common factor. So if you have a common factor, we can factor it out, right? Yeah. We do factorization. We factor the common factor out. That's a simple operation, right? Yeah. So let's do the factorization on the last 2 terms. So we can rewrite the last 2 terms in this new way by factoring common factor x out. Yeah. In this way, we change the structure of the given formula. Right? The structure is changed. If the structure is changed, but the value is not changed, right? The same value. We do not change the value, but we change the structure of the formula. That's important. The structure change is important because it would impact the number of multiplications. If we count the number of multiplications, before we change the structure, there are 3 multiplications. The first term, 1. The second term, 2. 1 plus 2 is 3. But after we change the structure, we only have 2 multiplications. X times parenthesis 1. A2 coefficient times x, that's 2. No more. Only these 2 multiplications. So you can see the number of multiplications are quite different. From 3 to 2. That's a big improvement. From 3 to 2. That's a big improvement. Okay? So the performance, by factorization, we get a gain, significant gain. That gain is from 3 multiplications to 2 multiplications. A good reduction. A good number of multiplication reduction. A significant improvement. So we're happy we get a promising intermediate result. This is intermediate result. We need to do more than that. But at least this step shows us some promising potential. Okay? Yeah, promising potential. Yeah. So along this direction, we feel we can get much better improvement if we along this successful direction. Okay? All right, so let me pause and stop the preparation part here, and next time I will complete the remaining part of Horner's rule. Okay, all right, so that's it.